All right, at the end of the lab, you're gonna have two crystals. Hopefully, one acidic compound, the other one is neutral compound. Okay. The next question is, how do you know or how you determine the identity of that crystal? Okay. All right. Let's say I have crystal biphenyl, but I don't know if it is biphenyl or not. Okay. So how do I come up with the determine the structure or the identity of this crystal? Here's how you do it. We have two techniques, okay, to do so. One we call infrared or IR spectroscopy. Now some of you might have touched the IR machine before, IR instrument. So there's a theory behind it. So if you go to Canvas, you're gonna see it right here. So it's a simple IR reading, mostly Tuskegee. Okay, read that just a little, all right? And once you read that, you're gonna understand how this works. Okay, so you're gonna take some of your crystal, add on to the IR machine on the sample holder, take an IR of it. You're gonna get the IR spectrum, look something like that. Okay, there are multiple unknowns, so those are different, but this is from biphenyl. Okay, so you're gonna read it, draw the line at 3000, nothing right below 3000. I'll say, oh, that's no sp3ch, no alkane here. There's a peak right above 3000 line, or tell you that's an sp2ch, that's an alkene. Okay, no hydroxyl group, no NH. You're gonna see it right here if you have one. All right. And what else we have? Draw the line at 1700. There's no C double bond O, no ketone, no aldehyde, no carboxylic acid. All right. And draw another line at about 2200. No triple bond whatsoever. And you look at right here. Oh, there's an overtone. Yep, that probably have benzene ring. Okay. Now you probably don't know right now. That's why you have to go back and read the reading on Canvas that I posted, and you're gonna understand what's going on in here. Okay. Let's say I have this information. All right. First of all, no carbonyl carbon at all, no C double bond, no. Which of these are not my crystal? Well, no C double bond, no. Benzyl got two C double bond, no. See that? 9-fluorinone got C double bond, no. Not these two. Okay. All right. So IR will help narrow down your option. What else not show up on this spectrum for sure? It comes in functional group. I'll take a look here. And the very first one I saw, so there's no alkane, sp3ch, right? In any of these, fluorine, biphenyl, and naphthalene, take a look. Fluorine had an sp3ch. That's just regular alkane, like CH bond of alkane. Okay. So IR tell you that you don't have that peak, so not fluorine. Basically, the IR tells you got only two options left, either biphenyl or naphthalene. Okay. Now, how do you differentiate between these two? Well, you're gonna use the melting range. Okay. So you have this in your handout. So right now, my options are narrowed down to just biphenyl and naphthalene, and you can see that these two compounds have different melting point. Okay, this is a melting point range. So we're gonna check the melting point. All right. So how to do that? Well, we're gonna pack your crystal in a small capillary tube, look like that. UTA will tell you how to pack the capillary tube. Okay. And once you have the capillary tube, well, we're gonna determine the melting range. Not really melting point anymore, but I'll tell you in a bit. So we determine the melting range and compare back to which one do you get basically. Okay. All right. A little bit about the theory behind or the concept behind the melting range. Okay, so melting point or melting range is a measure of strength of the intermolecular forces, like London forces, hydrogen bond, dipole, something like that, in a crystalline organic compound. Okay, so these are intermolecular forces, and you guys know the strength go up like that. All right. Here's the thing: if I have the compound, just pure compound, all this from the same intermolecular forces. Right? Well, same compound, same intermolecular forces. When I break some of these interactions, well, you like this solid lost some interaction, these molecules or these atoms won't hold to one another strongly. They will start melting to become liquid. Okay, and the theory is right here. All right, pure compounds have a sharp melting range, usually 0.5 to 1.5 degrees C apart. Okay, you're gonna see when it start melting and when it's completely melted. about 0.5 to 1.5 degrees apart, become that melting range behavior, right? But in this case, since you guys are new, we allow you 3 degrees apart. That's pure enough for us. Okay. Now, the impure compounds have either broad or depressed melting range. Broad means like they're gonna melt way too early. Okay, way too early and completely melted, usually at the same like certain temperature. Or depressed, start melting early, completely melted way too early than it's supposed to. The reason is this would happen. Okay, when your crystal, let's say your solid, is not pure, so of course it has some impurity, and this impurity are different molecules, different compounds. The intermolecular forces are different than the regular compounds. Could be weaker, could be stronger, doesn't matter. All right, but now, so basically we have different type of intermolecular forces. When you heat up, well, the weaker start uh, you are destroying the weaker intermolecular forces first. That's why you see the solid melting way too early. Okay, that's way too early. That's why you see either broad or depressed melting range. Okay, all right, that's about melting range, and do the packing capillary tube. On the next video, I'm going to teach you how to measure the melting range. Okay.